All right, today we'll be going over for the fucking fifth time. I've recorded this video twice now and managed to fuck it up both times. So we're gonna do this one last time. Statistical learning for big data. This is chapter 2, statistical learning workflow. Quick acknowledgement. And most of today will focus on the early part of this will focus on the business understanding. And then in the next video, we'll get into the rest of chapter 2 and a little bit more about data preparation, things of that nature. So a little bit about the business understanding. This is important because you you can apply the same data set in various different ways to solve different problems. Say I have an ice cream shop and I want to figure out peak sales, the hours of peak sale. Maybe this, which may determine the amount of staff I keep on hand, the inventory that I have ready, power consumption with the amount of freezers that are active, whatever I want to do with that information. But ultimately, I wanted to determine peak hours. So I use historical sales info, maybe from my database of customer interactions, and that database may have times, dates, maybe information about the weather outside, and personal information of everybody that bought ice cream in the shop. Um, that data can be used to either determine peak ice cream sales, or conversely, you can use it to denote or predict the demographic of your ice cream shop based off of the customer information. You can find, based off some type of statistical analysis, you can find patterns where, let's say, the average person that came in was 22, or they're more likely to be black than white, or whatever the case is. We can answer different questions with the same data. We just have to determine what goals we want to pursue and how we're going to utilize that data to solve those goals. So again, identifying goals is key, and then and this ultimately defines your data mining goals. If I'm gonna do demographic, guess what? I need to focus my data mining, my acquisition. That needs to be focused on personal information, not so much other things. And then of course we produce a project plan. We need to ask sharp questions, of course. It's just like setting smart goals, things that are measurable, things that are thought-provoking, um, versus vague questions. Ultimately, the questions that we ask and the goals that are set will determine the type of model that we'll be using, whether we're using classification or regression. So this is whether we're classifying in a into predetermined groups, or if we do some type of forecasting and prediction on future data. Prediction on future data. There you go. Some questions we can ask. Is this a binary classification? Is it a yes or a no, positive or a negative? If this will, of course, affect the type of model that you use, and how you structure the architecture of your model. One of the things we'll get into later is activation functions. And for binary classification, it's common that we use a sigmoid activation function in our final layer to produce a positive or negative classification. Um, so usually how a sigmoid function works, it's a probability curve from 0 to 1, and all the numbers in between. Of course, they're decimals, so they can be represented directly as percentages. And if you're above the 50% threshold, then it'll return true or positive. If you're below that 50% threshold, then you return negative. Another question we can ask, is this object unique? A lot of AI and machine learning is used for fraud detection or spam filters for emails. Does this match a typical format? Is this an anomaly? Some things, sometimes we'll get into this a little bit later, but anomalies can be difficult to detect at times, because just that they're unusual. They may be atypical in the data set, not have large amounts of representative data or instances or samples. Okay, those are all synonymous. Instances in the data or samples that can be used for training. So instead of training to detect the anomaly, instead of training to detect that, We train to detect dogs. We train to detect, come on, we train to detect the typical case. And if something doesn't match that case, then we say, we don't know what this is, but it's weird. Okay. When it comes to forecasting, we use regression algorithms. This takes historical data, trains off of that, finds correlations in the data, and then predicts future data based off historical averages. Sorry, averages probably isn't a good word to use there, but historical data. Clustering algorithms, of course, we can use this to determine what type of demographic, like certain movies, or separate things into categories. Uh, so how is this data organized? What patterns are inherent in the data that can be extracted? Then we have, of course, data understanding. First, we collect data. We describe the data via some statistics. Some really common statistical methods for analyzation are something we should all know: mode, median, range, and mean. I think, yeah, that's all of them. Those are all fairly simple means of statistical analysis and will unveil a decent bit about the data set. Um, then we explore data. We will visualize any issues with the data. Um, we look for patterns that may be somewhat obvious or inherent. That way we can gain an understanding of how we expect the model to perform off the set data. Then we verify the data quality with eliminating errors, outliers. So again, that anomaly or unusualness, and then any missing observations, which we'll get into a little bit later. Great book here. Recommend to read. It is still on my to-do list. I have not read this yet, full disclosure. Again, it's important that we focus on the structure of data, the quality of data, and descriptive statistics. And that way we have a way to visualize data. If we can visualize it, we can actually, as we'll see later, that models are merely mathematical representations of something. So if we're essentially making, for a data set, this is a complex way to make a best fit line or a trend line of data. We'll see an example of that a little bit later in the slides. The data are modified according to the analysis. We adjust for extreme outliers and observations. We estimate missing observations in a variety of ways. We transform variables and we form new variables. Ooh, I just farted. Here's a bit about data understanding. First, we're going to examine things to understand the gross or surface properties of the acquired data and report on the results with some sort of statistical summary. Let's take a little bit closer look at the data. We have different types of data. It comes in all forms and shapes and sizes. We have quantitative and qualitative data. Qualitative data is typically represented as some categorical or nominal variable. It's usually in some words. It may be a comment, maybe a name, maybe a gender, something like that. And then we have continuous variables that are typically quantitative and already in number form. Quantitative variables, continuous variables, are usually very easy to operate with, because in the end of the day, you have to keep in mind a computer understands the stream of ones and zeros. It operates in numbers. We have to find a way to enumerate our data, which we'll get into a little bit later as well. But to speak on that a little bit more now, it's very common that if you have a document and you're training a model like ChatGPT, a large language model, something that would try either attempt to perform like translation or chatbots or something like that, where language is like your key output, you're going to find a way to train this model with words, ultimately, because it's language. But we have to find a way to represent words as numbers. So typically what we'll do is a statistical analysis, maybe on raw word count. How many times does specific words, the word the, or the word boy, or the word ran, all show up in this document? And we would also attempt to quantify their context. Where are these words used in conjunction with others? And if we can find a way to enumerate that data, represent it as numbers, then we can start to train a model off of it. Data preparation. This is a very important phase and one of the most time-consuming phases of getting a model to work. So as we can see here, 60% of your time is spent cleaning and organizing data. We'll get into an issue that we find is garbage in, garbage out. We have to feed a model high quality data to ensure that we're getting the most accurate results. But yes, messy data is by far the most time consuming aspect of a typical data scientist workflow. Real world data is often dirty. It may lack uniqueness, so duplicate values. Things may be formatted improperly, such as the birth date. You may have invalid values or missing values altogether. You have misspelled values and things of this nature. These introduce extra noise or variance into the model that can lead to incorrect predictions. It can cause data to be inconsistent or incomplete. And we have various methods of dealing with this, but it does present a problem, and we have to correct all this before we even begin to train a model. Again, this is just another slide going all of the issues of dirty data. And here's the quote that I mentioned: garbage in, garbage out. We pre-process and pre-handle data in order to avoid this issue. Data cleaning, we fill in missing values. We have data reduction, where we sample data records with the attributes that closely align with our desired business goal. As I mentioned earlier, data can be used in a variety of different ways. It's up to us to determine how that data gets used. If I have an ice cream shop again and I want to determine the peak hours of sales, it makes sense that I would want sale data and time data. But what I don't need for that particular task, guess what? Is personal data. I don't need to know anything about the who came in and bought ice cream. I just need to know how many came in and bought ice cream. So therefore, if we have this large data set of ice cream sold, customer information, and then time of day, I can eliminate customer data altogether, which saves me computational time. It saves me memory because I don't have to store personal data. This is that data reduction. We pick attributes, so again, ice cream sales and time that are relevant to our problem. We have text cleaning, so we get rid of extraneous embedded characters, underscores, dollar signs, things of that nature. We enumerate data. We have data discretization, discretization, where we convert things in the continuous domain to the discrete domain. The continuous domain is like a sinusoidal wave, how everything connects, and it's like your typical function, a graph of your function. Discrete data is data that occurs via instances. A specific instance in time can be tracked. It's usually a uh series, no, not series, what's the fixed interval, a fixed interval of time between each measured event. So usually a discrete instance could look like revenue for what am I trying to do here? Revenue for a restaurant. We have revenue each month. Each month is a discrete thing, uh, a discrete instance. And then you have data normalization. We reduce dimensions and noise. This is similar to data reduction. We have to pre-process data. We have to clean it. We have to make sure, again, fill in missing values, things of that nature. And some of the methods that we use to pre-process data includes deletion. So as we can see, highlighted here, we have this row of Nick. Nick here, he has no values filled in. Instead of trying to estimate or putting in random values that may skew the data set, we'll just delete Nick's entry because it's more of a hassle to figure out what's going in for his entire row and have a completely fabricated row, and just get rid of him. So we delete. We have dummy substitution, which is essentially just random substitution with some random categorical or some numerical value. Then you have mean substitution. Let's say we have an age. Somebody is missing an age, such as Nick. We could take the average value of all the known participants and then fill him in with the average age. That way, it doesn't skew the data set. And it just operates on the average that is already present. But by adding in that mean substitution, we have one more sample to train our model with. So deletion isn't always the key because ultimately you need data to train off of. If you delete it all because it's imprecise or doesn't have the fields needed, you're not going to have enough data to train with. So deletion isn't always the key. Sometimes substitution is needed. Um, so yeah, again, and that mean, think average. It's an average substitution. We take the average of the data set for a given attribute or a given feature. So this whole thing is the data set. The data set is made up of attributes such as name, right? Such as age. These are attributes or features of the data set. We just calculate the average of a feature or an attribute, and then we, of course, insert it. We have frequent substitution, which is instead of the mean, guess what? We're using the mode, okay? Um, this is how many times is this, what is the most frequent data? Let's say we have a couple people, so it looks like 21 in this column here was repeated. This may be the mode of the data. This may be a commonality. So we'll just, for the missing values, instead of the mean, we put in the mode, how frequent something occurred in the data set. And then, of course, we have regression substitution, or we replace missing values with regressed calculated values. Something we should know about outliers and anomalies. At times, outliers and anomalies can be useful for our data. At times, they can only lead us astray. It is completely subjective. An example I would give to this is if you want to find the average distance that an American travels in their car on a yearly basis, we could collect data. And if we have, let's say the average comes out to about the average American drives like 50,000 miles in a year. But then you have one guy that drives 1,000,000 miles. And this could be true. You could have a guy that drives that much. But based off your problem, are we doing outlier detection, or is this to predict and forecast the average based off some other data? That outlier may lead us astray, or it may be helpful in anomaly detection. Depends on what your business case is. Okay. But that being said, sometimes you have to look at the absurdity of the outlier. Okay. The Earth's circumference is 25,000 miles to go around the Earth. If you're driving 1,000,000 miles, that means you've circled the Earth. What is that? 4 times in 100,000. You've circled the Earth 40 times in a year. It just doesn't sound right. It sounds absurd. So we may discount that as just so yeah, we don't want that absurd value to skew the model's interpretation. Outliers can be somewhat common, and what considered an outlier is subjective, but they can make your model more robust. But they can also be a result of bad data collection and be illegitimate. And they could, again, skew that data set. Then we get to data reduction. We do record sampling. We sample data records and choose the representative subset of data. We do attribute sampling. We select the most important attributes or features, again, from the data, as I mentioned in this table, the age, the date, the time. If I'm selling ice cream, what do I need? We have aggregation. We divide the data into groups and store the numbers of each group. So, for example, if you have a restaurant that has daily sales, what's the word I'm looking for? We summarize, we concatenate that daily sales into monthly sales. That way you don't have as many discrete data points, and it's still representative of sales of the restaurant, but it's done so on a different timeline. This will ultimately save, by reducing data, you reduce computational complexity. Instead of having doing a daily analysis, you can do a monthly analysis, and it'll still achieve a similar goal of forecasting. Let's see. Yeah, so more data can result in much longer run times for algorithms and larger computational and memory requirements. All right, that's the key. AI can take days, months, and weeks to train. It can consume large amounts of power. We have to find a way at times to reduce our data and make that training process more efficient. Then we get into feature engineering, which is sort of an art. This is the balancing act of finding and including informative variables while avoiding too many unrelated variables. Okay. Um, this also has to deal with a bit of formatting. Instead of having a string date and feeding in a categorical variable, what we could do is we do some feature engineering to break the data up into discrete instances of day, year, month, represent them numerically. And that's a form of feature engineering. We make new features from existing features. Informative variables can improve our result, while unrelated variables introduce unnecessary noise to the model. Feature engineering, attribute selection, very similar. Ultimately, what it attempts to do is reduce the size of our data, reduce computational complexity and memory requirements, and yeah. It is worth noting that oftentimes data scientists interact with domain experts because that way we have an understanding of the data. If I look at medical diagnostic imagery, I don't necessarily know what I'm looking at, but with the help of a physician or a radiologist, I can look at something, determine um, um, and have a better understanding of the data, what I'm looking for, and how this plays into the ultimate goal. A feature is an individual measurable property of a characteristic or a phenomenon that's being observed. So here we have all of our features, okay? The target is also a feature, but it's a special feature because it's a dependent variable. This is what we're attempting to measure. This is the target, okay? We have various amounts of bedrooms, the square footage of a home, the neighborhood that is found, and then price data. We use these features to determine to predict in the future the price point or the sales price of a house given its neighborhood, square footage, and house size. So for example, in this last row, based off some intuition, we can see that other four bedroom homes with similar square footage sold in this range of 150,000 to 270,000. However, it's worth noting that in normal town, it appears there any normal town in normal town that prices may be a little bit higher based off of the neighborhood and the bedroom count. So a healthy prediction may be um it's going to be in the range of 150 to 270, and it's going to be maybe this is a little bit less square footage but it has an extra bed. I would expect a price of about $230,000. um that is the process that your machine goes through. This is an example of using features to determine a target. Um, but we don't understand the question that we seek to answer with AI and machine learning is how much weight, you'll hear this term a lot, how much weight, how much credence, how much how much weight does each feature have on the ultimate decision that's made, on the target, on the dependent variable? How much does bedroom contribute to sales price? How much does square footage contribute to the sales price? Or how much does the neighborhood contribute to sales price? AI attempts to find correlations and assign weights to parts of that decision making. We find the coefficients, we find the probability that, okay, if all we're concerned about is the bedroom count, then we would see on average, higher prices for higher bedrooms. But maybe that's not the case. Maybe sales prices heavily influenced by neighborhood. We just find a way to measure the significance of each feature and then predict based off of that. Feature engineering can augment your data. We create additional relevant features from the existing raw features in the data. An example of this would be, like I said, the date. We break it up into different variables. We create new variables, additional features from the original. All right. And then we have creating dummy variables. We enumerate a categorical variable to represent it in a number format that may be more palatable to a computer or information system. Um, and creating dummy variables is more common with categorical things. So here we have the performance results of models based on 4 training set. Um, and these are different these are different cost functions. Okay. Cost functions, as I went over in a previous video, merely measure the difference, but now there are different types of cost functions, but ultimately what they do is they measure the difference between the expected output and the output that was, well, produced by the model. We measure the difference between the real and the guess, and then we find some we adjust the model to shrink this cost. We ultimately want to reduce the cost or loss function to zero, because if we can reduce it to zero, what happens? Think about what that means. If the difference if the difference is zero between the real value that we know that we've observed in the real world, the data, and the inference, that means our model is 100% accurate. It's accurately representing and predicting data in the real world. Now, granted, this won't happen in real life, but that's what we seek to do, is minimize the cost function. Okay. Um, Feature selection, we select a subset of features from the original data, reduces dimensionality by using a minimal set of features to represent the maximum amount of variance in the data. The subset of features are then the only features to be included when training the model. Normally, feature engineering is applied first to generate additional features. Okay. Some of the benefits include simplification of models, shorter training times via reducing computational complexity to avoid the curse of dimensionality, which we'll get into in previous slides, or in the future slides, and then enhance generalization by reducing overfitting, which we'll talk about later as well. Feature selection versus dimension reduction. Okay, feature selection and then engineering. It does not inherently seek to reduce the number of features in the data set. Um, it's usually not referred to by the term dimensionality reduction, but it does reduce the dimensions of the data. Feature selection extracts a subset of original features or attributes of data without changing them. We're not making anything new. It's just I pick and choose what data I want to use. Again, ice cream example. If I'm predicting times of day, the peak hours of sale, I need time data and I need sales info. If I'm computing the demographic and I want to know the race of the next person to walk through my door, then I need customer information. I need age, I need race, I need X, Y, and Z. I need data about the particular thing that I'm trying to measure. And I'm not going to use extraneous data because it introduces noise and computational complexity that isn't required for solving the problem. Dimensionality reduction employs engineered features, okay? Engineered features that can transform the original features and thus modify them. Examples of dimensionality reduction include principal component analysis, canonical correlation analysis, and then singular value deposition. The process of machine learning flows like this. We have raw data. We process and develop features iteratively until we come to the prepared data. Then we train the model on that prepared data, And we iterate this multiple times. We iterate through the data set. We may iterate over different types of models until we come to the candidate model, and then we deploy it to the real world where we'll see it actually operate on future real world data, and we can evaluate its performance there. Now, what is a model? I love this quote down here. This is key. All models are wrong, but some are useful. This is disgustingly true. Okay. Look at this. This is a trend line. This is that models speak about the general. They speak about trends. Okay. If I have stocks, if I want to make an AI model to predict stocks, this AI model will probably never land on the exact price point of what a stock is going to sell for on a particular day. But you know what it will do? Over time, we'll see a trend in stock price, which can accurately give us like it can give us a high level understanding or simplification of the real world data that we can act off of. It predicts trends, it generalizes. It is the forecasts are never going to be 100% accurate, but it gives you an idea in which way something's going. Models are always wrong because they speak to the general. They're not used for highly unusual, anomaly, outlier data. It's not. It predicts the commonalities. It finds the patterns, and it speaks to those patterns that we can then inference from. Okay. Um, that's ultimately what it does. It's a mathematical model that generates predictions by finding patterns. Okay. Um, at a high level, a model is a simplification of something more complex. Machine learning algorithm uses data automatically to learn the rules. It simplifies the complexity of data into relationships described by the rules. And modeling is part art, part science. Um, always keep that in mind. I am going to give a quick math lesson here. I will share my screen as a whole. I will then paint. All right, quick math lesson. I want you to keep in mind this visualization of the graph, okay? So imagine I have a polynomial, all right? Just a function of multiple terms. I have a plus bx plus c x squared dot dot dot. This can continue ad infinitum until some letter z, okay, x to the n, okay? And this is just some exponent here. Now, this is your polynomial. This is your mathematical function that we're finding. And this will represent the graph. This is a graphable function, okay, that we saw here. This is this line that equation will graph to a line, a trend line that will describe our data, okay? Now, it is important to understand that AI models, what are we computing? Okay, like I mentioned earlier, we're computing the uh decision, the weights of a particular feature, attribute, or an input. Okay, these are all synonymous. Again, the features of our data are inputs, the age, the temperature, the sales information, the pixels of an image. Okay, these those are our features, right? We want to determine how much weight should be given to a particular feature when making a decision. How much does bedroom contribute to the overall price of a house? How much does square footage contribute, all right, to the price point? So what are we doing? So in these equations, these very long, complex equations, guess what? X is representative of our input. These are our inputs. These are our features, okay? Now, if X is given to us by the data, what does A, B, C, D, E to Z, what does this represent? Those are our weights. those are the decisions that we'll make. Those are the weights of the decisions. Okay. I'm sorry, the weights of the features that ultimately lead to a decision. Okay. This is how much weight do we put on, let's say this is xi, sorry, subscript I. This is xj, subscript j. Let's say this is bedroom count. Let's say xi is bedroom count. Let's say xj is square footage. Okay. So we have square. Oof, forgive me. Paint is not my friend. Square feet, and then we just have rooms. All right. Now, if bedrooms aren't that big a deal, then we would have a lower coefficient, a lower weight. Let's say it only contributes to 10%, so 0.1. That would be B, okay? That would be B. That's our coefficient, that's our weight of the decision. But let's say square footage is a huge factor and it contributes to 70%. So 0.7%, 70% of the decision. All right. So it's going to give in the calculation of the cost of a home in this calculation, this variable is going to contribute more significantly to the outcome of the cost than xi will, than the room count will. Okay. And then A here, you notice that there's no X next to it. There's no input on this. This is referred to as your bias. Now, technically, if you want to get technical in this math, there is technically an X to the 0 here. But as we know, anything to the power of 0 is 1. Therefore, 1 and 1 times any number is itself. So therefore, we don't include this x to the 0. Same way that this is x squared, this is technically x to the 1. Any power to the any variable or number to the power of 1 is itself. So we just don't write it. But it's a series, okay? And this right here, this bias may be it's almost like the y-intercept of a graph. It's like your starting point. Let's say in a particular area, a house will never go less than $100,000. Then your bias is going to be 100,000. That's going to be your starting point. And then the decisions and factors that contribute past that will increase the house price from there. That's what your bias is, okay? Let me see. Now, another thing I want to get into. You'll notice that this is z times x to the n, right? This polynomial this is dependent on the amount of features that we have of our data. Now, this is also referred to as dimensionality. The amount of features that we have directly correlates to the complexity of our data. The number of features contributes to our dimensionality. Now, if we have, let's say I have data. What color should I'll use red. Let's say I have some data points here, right? Boop, 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 boop. And they generally trend like this. We have a couple outliers, but they generally trend down. Now, a simple linear regression model, all right, will find a best fit line. Imagine that's perfectly straight. It's a linear model. It goes straight down. And this is given by the equation y equals mx plus b, okay? Where b is literally our bias, x is our given inputs. So I don't know, like house, again, bedrooms. If we're only considering bedrooms, and that's the only simple feature we're considering, we're not going to consider neighborhood of square footage, which is just going to be a univariable decision, then this linear model is more than sufficient. Okay. Where x is the input, b is the bias, and m is the weight. This is typically it's referred to as the slope of a line, but this is it's the rate. It's the slope. It's the weight that affects the input. And we, in machine learning, we attempt to calculate this M that fits the data well. Okay. And ultimately will lead to Y, which is the house price. All right. Now, as data gets more and more complex and we have higher dimensions of data, look up here. This is X to the 1. We have a bias and we have X to the 1, right? Just like up here. Okay. Just like up here. We have our bias, X to the 0 times X to the 1 with some coefficient. As data gets more and more complex, we need more dimensions, more features to accurately represent data. Let's say I have data that's in the form of a parabola, right? And I attempt to solve this using linear regression. Look at the problem here. My line, I cannot possibly encapsulate all the data here. No matter what angle I draw this at, I will miss an infinite amount of data that's going this way, that's going off in the negative X direction. I will miss infinite amounts of data. Or if I draw the line down, I will miss infinite amounts of data in the positive X direction up here. So guess what? Our model has to expand in complexity in order to handle more complex data. Let me delete that. Okay. So guess what that means? We have to add more coefficients and more inputs and more features and more dimensions to accurately model. So the parent function here of a parabola, as we may know, is y is equal to x squared. This is the parent function. All right. We can do many different things to the parabola, right? We can reflect it by making this negative. We can invert it over the x-axis. We can flip it over the y. We can translate it up, and things of that nature. All right. We can do all that to x squared to get it to represent data better. But let's say we have a different graph. Let's say we have data that is plotted like this. Let's say we have boop, 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 boop. Okay. Now, of course, the best line here, if I try to model this data, no, yeah, if I'm going to model this data, I could use a parabola, but I'm missing. It's not very accurate with certain cases. So I need to find something that fits the data better. And a way that we can do this intuitively based off our data, we can pick a function to accurately represent the complexity. So if you notice, this is going to get into a bit of concepts of calculus, not actual math, but we look at POIs. POIs. These are points of inflection where the graph changes concavity, okay? Now that's a fancy way of saying this graph turns. So as we can see, we're going down, down, down. This is a negative slope. We hit this minimum point and we come up. It changes concavity. We've hit a point of inflection. So now we're positive, positive, positive. This points of inflection are just to say the graph changes slope from positive to negative. It's increasing versus it's decreasing. That's all that means. Now we're increasing, 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 hit a maximum. Now we're decreasing, again, another point of concavity here. We're decreasing, decreasing, decreasing. We hit another point, minimum, back up, back up, back up. There are 3 points of concavity in this data. So how can we find something that will accurately model this? Well, this gets into math, but I know that I know this, that the points of inflection of a graph are directly correlated to the degree of the polynomial that represents it. And what I mean by that is the points of inflection are equal to x to the n minus 1. Okay? Think about this. X squared is a parabola. How many points of inflections does x squared have? Let's see. It decreases, 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 hits a point of inflection, and increases, increases until infinity. X squared minus 1 is 1 in the exponent, that is. X squared minus 1 in the exponent, that means there can only be 1 point of inflection in this graph. And it only has 1 point. X squared will only ever have 1 point. So to have 3 points of inflection, this graph must be represented by a polynomial of a minimum of to the power of 4, right? And then we have some terms after it, bx cubed plus cx squared, right? That ultimately will contribute to the shape of the graph to make it, because where's my brushes? Because as we know, the parent function of x squared, x to the fourth is just a parabola again, but it's really steep. It's a steeper increase than x squared, just because if you put something to the fourth power, 2 to the 4 is what, 16, versus 2 squared is 4, right? It increases at a faster rate. So that being said, but the parent function is similar to x squared, but we add on additional coefficients and modifiers to the graph to translate it and get different values. But this has to be represented by a polynomial of the 4th degree. So that means we need to have features that allow us to represent this polynomial. We have to at least have 4 features of this data. Okay? The complexity of our data increased, the complexity of our model increased. The polynomial, we added more terms to the polynomial, all right? A term is just the collection of the coefficient and the input. That's all this is, all right? That's a bit heavy on the math side and how this all works. But yeah, that's for your basic math understanding of how this all functions. It's worth noting that, as I said, this is x to the 4th. It looks exactly like x squared, but it's steeper, okay? X to the 4th the parent function only has 1 point of inflection. X to the 4th does not have to utilize all of its points, but it has the capability of using all of its points. It is possible that for a simple linear regression, that I use a model that has that's a 4th degree polynomial. It's possible, but it's overkill for the model. Again, models are not exact. Models are meant to predict trends. And if a linear model that's simple and easy to train accurately predicts a trend, there's no need to have a 4th degree polynomial that's represented and do massively large calculations. There's no point. Visualizing the data, graphing it, and kind of figuring out intuitively how you can best represent it in your model is key, is all I wanted to say here. And I'll save this. Anyway, enough of that. Back to my point. Oh, ignore my screen. Hello? I'm gonna switch back to only sharing the screen. Read mode. All right. And then I'm sorry again, that was a bit of a long-winded explanation. How to develop a model. Of course, we have historical data. We split it into data, training data and testing data. About 60 to 80% of data is used for training, while 20 to 40% is used for verification purposes after the model has been trained. We generate a model, evaluate said model, and then once we have that model, we apply future data and receive the actual prediction results. This algorithm will learn from the training data and the patterns present there, and then map the features to the target based off various weights. An example of splitting the data set occurs here. We split this data set. We use 2 of these for verification and validation and train the model off the rest of these points. And then we're going to predict if a customer is going to switch to another supplier, so whether they churn or not. This is a binary classification. It's a yes or a no. The training set estimation, the validation set. And then here is a great example of, again, as I mentioned, binary classification usually uses the sigmoid activation function, which is a probabilistic curve of from 0 to 1. Okay, I'll actually paint that real quick just because I'm feeling real fucking nerdy today. I'm feeling like a little fucking geek at the moment. This math shit got me excited. All right. We have a sigmoid function that typically looks like this. Okay. And we have some threshold. This is our threshold of 0.5. This sigmoid, it looks like a little S too, little funny mnemonic device. That way you can remember it. But as you can see here, where's my, oh, I was not sharing my paint screen. Okay, sorry. Let me go share my screen real quick. Paint. Sorry. You should be able to see my paint screen now. This is the sigmoid function. Okay. This, and then the threshold of 0.5. Things above in this area are classified as true. Things in this area classified as false. All right. And we have to, of course, we reach that threshold, and that threshold is used in classification. That is a great segue into this. If the city is Miami, we determine that city plays a large role in determining whether a supplier or a customer is going to churn and switch suppliers. If they're found in Miami, we add 0.7 to their score. We determine that if they're in Miami, there's a strong possibility that they will leave us. All right. Versus if the city is Orlando, there's a low possibility they'll leave us. And you see how these are decimals because it's based off of probability. And we sum these up. We do a sum. Oh, sorry. I was going to try to draw on this. We do a summation. Oh, can I draw? Oh my God, I can draw on Zoom? Oh my fucking heavens. Heavens to Betsy. Oh my God. Okay, anyway. I just got excited. Fuck Paint. Okay. All respect to Microsoft. We do a summation of all these statements at the end and then determine, does the probability exceed 0.5? If so, then there's a likelihood that they will churn. If it does not exceed that threshold, then no, they won't churn. Easy enough. How do I erase it? Can I just Control Z this? Oh, I can. It's amazing. All right, cool. And we'll kind of stop there for today. That's been enough of that. Tune in and finish this chapter a little bit later. But I think that was, yeah, that was good. Anyway, catch you guys later. Adios.